Hi, we present to you a vision-based driver assist system for dashcams. According to a survey, around 94% of all crashes were due to human errors and the rest due to mechanical and environmental failures. These vision-based systems are saving around 20,000 lives a day and is set to reach a market potential of $9.69 billion by the year 2023. Our goal for this project is to implement an all-in-one driver's assist solution that can make use of readily available dashcams capable of doing the following tasks. Lane change maneuvering and forward collision avoidance by top-down view, lane departure warnings, collision warnings and obstacle warnings, side lane monitoring, multi-view scalability, and speed detection. Aditya will begin speaking about the top-down view and lane detection.
Okay, so first what we do is we have our input image and then we define a region of interest manually. We hard code the region of interest because we don't have the camera parameters and therefore we don't have camera calibration. Once we hard code a region of interest, we transform it to get the bird's eye view. We choose 4 points on the input image and then we transform that to get the bird's eye view. Subsequently, we find the canny edge detection for both the input image and the bird's eye view image. Once we find the canny edge, we then use huff transforms to find straight lines from the canny edge map. Sometimes there is a case where you have two lines, one continuous line and a broken line. So in those cases, what we do is we find the average line. Now, since we have a top-down view, we know the number of pixels between the two lanes. So we use these pixels to calculate the distance between the two lanes by scaling it accordingly. Once we calculate the distance between the two lanes, we assume that the camera is mounted in the center of the car, and using that we calculate the offset of the car from the center of the lane. To calculate the radius of curvature, we use the top-down view, and we've discretized our best fit line that we found earlier into 9 windows. We use something called a sliding window technique. We then fit a second order polynomial to get the best fit polynomial and the best fit curve. Now, since we have two curves, we find the average radii of the two curves to calculate the radius of curvature. Once we find the radius of curvature as well as the distance between the two lanes and the offset from the center of the lane, we then integrate all these features onto our input image and then display it. So this is as far as lane detection and lane centering is concerned. Ahmed will continue with the object tracking and object detection.
With the lanes detected, the next step in our pipeline is to detect the objects in our system. So we need to detect any obstacles that we might have in the environment. This includes pedestrians, motorcycles, buses, trucks, vehicles, and so on. We surveyed a ton of data sets before finally agreeing on using the COCO dataset, simply because it was the most balanced in terms of having the actual labels that we wanted, as well as not being too large in the sense that we wouldn't be able to use it, or that we would need too complex of a model to be able to classify the models, to classify the images. Such examples would be like ImageNet, which contains more than almost 1,000 classes. So COCO, on the other hand, uses 80 classes, which is much more manageable as compared to that. So with the data set selected, we wanted to select the best object detection model that we can use. And to do that, we surveyed several different models before selecting one to be our candidate. The 3 different models that we used were first MobileNet SSD, the 3rd version. And the reason we used that model is because it is very lightweight. It's meant to be run on mobile phones as well as embedded systems. And in terms of runtime, it was able to achieve the best performance in terms of speed as compared to the 2 other models that we used. However, as we can see in the image just on the screen, it suffers from being inaccurate in the sense that it can detect 2 objects when there exists only one, then that is even after applying non-maximal suppression. And it also suffers from not being accurate in the all detected objects, as can be seen for the white SUV. With that said, we wanted to explore other more accurate models, and the first model that we encountered was YOLO. YOLO is a very popular family of object detection architectures. And the one we used was YOLO V5N, which refers to the nano version of the YOLO V5. And the reason we used the V5N because it was the most lightweight to run of the different versions available. And the other versions include V5M for medium and so on. So with that model used, we can see that we get much cleaner detections, as can be seen for the traffic lights as well as the cars. And it provides pretty consistent performance. However, after discussing the results with Dr. Giambo, we were suggested to look at more state-of-the-art machine learning models that were anchor-free instead of anchor-based, like the two we have just discussed. And with that said, we decided to look at CenterNet. And the main advantage that CenterNet has, alongside being anchor-free, is that it is very accurate and capable of detecting objects that are very far away as compared to YOLO or MobileNet, which are limited in range of detections. And we can see this, in fact, where CenterNet can detect different cars in more obstructed environments, as can be seen in the parkway here, or even further down the lane in the image. So with CenterNet chosen, we decided to run our code and see how well it performs in terms of runtime. Because MobileNet provided the best runtime, we could run it on a CPU and achieve faster than a real-time speed. YOLO V5 was able to achieve real-time speed using a GPU, while on a CPU it was limited to around 60 frames per second, which was really suitable for our application. Whereas CenterNet suffered the most when it came to performance, albeit this was expected because it provided the best accuracy. So with CenterNet being used, we were very limited in processing power because we needed a very powerful machine to be able to use this model. Even with running a very top-of-the-line laptop, we were still suffering from 20 frames a second footage or even less at times. So to counteract this, we wanted to use some kind of interpolation that would allow us to use the detection only once every few frames instead of once every frame. And this is because we came in with the intuition that information is not being changed that much between two different frames. And if we can use something that could interpolate the centers or the objects, locations between these frames, then it would make our lives much easier and decrease the time. So with this intuition in mind, the very natural thing to use was optical flow, and optical flow performed miraculously well. So simply put, we just got the masks from the image, from the detections of CenterNet, applied them to the image, and found features of interest using the SIFT trackers, using these masks, and we then tracked those features in the image between the two different frames. However, we found that we could further improve on this algorithm by getting rid of the mask and the SIFT features and simply relying on the centers from CenterNet to be our guides, because CenterNet already detects those features. So with that, we could just use optical flow with the centers and then shift the bounding boxes as the centers move. However, we can see that when we're moving the bounding boxes, we could suffer from a bit of corruption, and that's a result of occlusion, where some cars go out of view when they're when they're obstructed by a different car. So with that said, we decided to get rid of the bounding box interpolation and just rely on the center interpolations, which provided pretty robust object tracking. And here we can see the center interpolation in action, where we can see the trails of the different cars that were detected being tracked, and here as well for the Tesla. So with that said, we can combine both algorithms together. So we have the lane detection and the object detection, and with that we have the final system running pretty fast, almost okay. So combining these two systems with the interpolation, we were able to run our object detection with tracking as well as detecting the lanes in real-time processing without requiring too much workload on the laptop. And mind you, we were only using 600 megabytes of VRAM, which is pretty reasonable for modern day GPUs. So with lane and obstacle detection experimented with, we wanted to also experiment with path planning potentially using road segmentation. However, we realized that we can't afford more inference in our pipeline, so we wanted to avoid learning-based approaches. So we experimented with two different model-free approaches for road segmentation. The first was k-means, that can be seen on the right, and the other was watershed segmentation, seen on the left. However, even though these two images might look pretty good for segmentation, these were ideal cases where noise was not present. And in regular operations, we had considerable noise, and it was not robust enough for us to do any motion planning on this sort of segmentation. And with that said, considering the constrained resources that we have, we decided not to go further with motion planning and instead rely on just object detection and collision.
Coming to speed estimation, given a video of a front dashboard camera, our task is to predict the speed of the vehicle using dense optical flow and a neural net to train on this. So why do we use dense optical flow? If we train with the original image or the original video itself, the model will simply tend to overfit because it will try to memorize every single image with a speed value. So in order to make a useful input feature to train on, we look into dense optical flow, as you can see in the next video. So what optical flow does, it takes 2 consecutive frames of a video and compares the change in the positions and speed compared to the previous frame. And calculating the relative velocity of the vehicle directly from an optical flow requires depth. In our case, the only way to estimate depth would be to use a neural network. However, as you can see, each frame extracts from the video is not completely useful, such as you have the sky and the dashboard, and these do not contribute necessarily to the estimation of speed. So we will be cropping out this part of the image, as you can find in our GitHub link, to a square, and then feeding this to a big neural network. We also try to improve the results by using a Kalman filter to smooth out the predictions by the network. As you can see, after efficient training, we managed to surpass the efficiency and the loss, and minimize the loss compared to the GitHub repo from which we were inspired by. Coming to the future plans, Ahmed is going to take over.
What does the future hold for this project? Given that what we've reached so far, we want to further expand the application by providing multi-view scalability, in the sense that if we can have access to reliable multi-view footage, we can stitch these images together and run our pipeline on the stitched image in the end. But the reason we weren't able to do this is that we weren't able to get our hands on free, reliable multi-view footage. The second thing that we want to expand on is actually providing the user with warnings. So these could include lane departure warnings, which we are already calculating how far away from the center we are, as well as collision detection or collision warnings, forward collision warnings, in where we just warn the user where if he's still, and forward collision warnings that provide the user with a warning if he or she are going to collide with the vehicle in front of them, based on the speed estimate as well as the tracked objects that we just found. Finally, we want to further optimize the speed estimation model, because as it stands now, it's a standalone feature because the model was not able to be run in parallel with the center net because we weren't able to fit both models on the same GPU. And with that said, our presentation comes to an end. Thank you for listening.